Alex.
How you open? How do you open? Hajimashou.
So today is a control group meeting?
Yes, yes, yes.
Really? I didn't check this.
We changed last time.
Okay, sorry.
大丈夫です。
Okay, shall we start?
はい。
Okay, Zafira-san, you start first.
So last time we discussed about to combine viscoelastic and friction damper. So here there's some flow chart. So first we have to determine the demand capacity for the damper in coupling beam. And then we have to design the viscoelastic and the friction damper based on required capacity. And then we have to check the coupling beam deformation compared with the damper deformations. And then we need strategy analysis, and then we check with displacement smith design and compare with DHA. So we thinking about a few concepts. So the first one, this one is viscoelastic material. And on the right side is the friction damper. Can you see properly? Can you see properly? So here.
Yeah.
So this is concept number one. We doesn't know which one we should choose. So it deform vertically. On the right side, we have 4 bolt of friction damper with the spring washer. And on the left side, we have viscoelastic damper. This 4 bolt is just to hold. It doesn't act like a friction damper. It's just to hold the viscoelastic in place. So it doesn't separate when it deforms. And then this is the plan view. This is the plan view. So we can just use 2 layer of viscoelastic material. And for the friction pad also, the friction damper, they also have a friction pad. And this is concept number 2, I was thinking. So for the friction damper, it can deform vertically. For viscoelastic, it can deform horizontally. And
How it works?
how it works?
I mean, can you draw the picture of deformation.
Formation. So this one able to go on this side, and this it can counter for axial load. So this is for shear.
But can you draw the picture?
Show the picture.
Suppose
So it goes
ball is
deform like this.
hmm? Hmm.
For this one can be deformed. One's go down
Mhm.
and one's go up. Another one go up. But this is only vertical deformation.
Deformation.
Vertical. One's go up and one go down. And this one is two direction. One's go up and this also can counter for axial load.
Hmm. So
And
friction damper is attached to which part of the beam?
one more time, Sensei. Which
Friction damper is attached. I mean,
this
there's a so beam is separated
yes.
in the middle,
Yes.
right?
Yes.
So, so friction damper is えっと、
This was the idea we discussed last time. So one side is friction damper, another one is viscoelastic.
so this is one steel panel.
One steel panel.
Is that correct?
This is the from the plan view, the cross section. So we have two support beam, left and right, and this is the friction damper, and this is viscoelastic.
So the plate connecting friction damper and the viscoelastic damper are same plate.
Yes.
Yes.
Yes, Sensei. These two panel, right, Sensei?
These two plates are common.
Yes. This is one.
And so I cannot imagine how it moves.
So supposedly should be one go down up, and this one should be go down when the wall will push this way. So this wall will go like this.
No.
And then it will go down.
No.
So one go up and then one go down.
And could you draw a picture of plate? I mean, friction damper and the viscoelastic damper is.
So should be like this. So this one will be close to here, and this side will be close to this side.
Okay. Anyway, could you draw exactly? I mean,
The deformation.
information of the
Okay. On the screen
No. Later.
later.
Not
Okay.
handwriting.
Okay.
Okay, but I understand the concept. Okay.
Okay. And then And here I also find a few papers that determine how to calculate for the for the friction damper. So first we have to determine the tightening force of the bolt, and then we can determine the friction force of the damper. And most of the paper, the maximum friction bolt is about 200 kilonewton. And this is how we calculate the deformation of the damper or the beam by the deflections of the wall and coupling beams. And my question here is how we going to, if we want to make two different damper in the middle of the beam, how we can put input in the Stera 3D. And because now we have for friction damper we can use bilinear surfaces, and for viscoelastic also we have a viscoelastic input. But what if we combine two damper in one element?
Yeah, we must change Stera 3D. Yeah.
Okay.
Okay.
Okay. That's all. Yeah, that's all for today. And I also prepare a slide for the GES. I will send you later. You can check. Okay, Simpson. Thank you so much.
Oh, you can present here.
Now? Okay.
Yeah.
I will open.
How much time you have?
How much time?
Yeah.
I don't. For today, I don't have anything.
No. In JES.
Oh, only 12 minutes, I think, for presentation. For one slot, 12 minutes.
12 minutes?
Yeah.
Including discussion?
Discussion, I think about 5 minutes.
So in total, 70 minutes?
Around that.
Oh, but you must make sure.
Okay.
And you prepare the slide to fit.
発表が8分です。
Oh, so you only have 8 minutes for
8
presentation.
minutes for presentation. Not including the question, right?
Only for presentation, 4 minutes for question and answer.
Okay. So here I have 16 slides. So first I explain the concept of our structure and displacement-based design. So for multi-degree, we convert to single degree of freedom, and we use the displacement-based design method graph to determine the capacity of the building. And this is the system of that we propose. So we have a couple structural wall with two different damper and a hybrid damper, and we want to check the performance of the systems. And this is a simple explanation about how the performance change after we put the damper. And here I explain about the basic from the steel damper. So we use two types, one of 750 times 350 steel coupling, and then after that.
This is not the steel damper. This is just only steel beam, right?
Steel beam, yes, steel beam only. So we want to determine the capacity for the damper to have. So we use the steel beam, and after that we apply for metallic damper, viscoelastic damper, and hybrid damper. And then I explain how we can apply the displacement-based design method. So first we have the model itself from Stera 3D, and then we determine the drift limit. After that, we calculate the damping ratio. After that, we find the effective displacement and the spectrum reduction. From there, we can find the effective period. And from the effective period, we can determine the displacement-based design curve. And after that, the design earthquake that we use for time history analysis. And after that, I explain about the result. First, we have the metallic damper. I compare 100% and 20%. After that, I compare with the THA. And after that, I discuss about viscoelastic damper. And then I compare with THA. And after that, the lastly is the combinations.
Well, Zafira-san,
Right.
how to say?
Mm.
It looks the same slide.
Seems like
Yeah,
Right.
yeah.
maybe I should
Well,
change the title.
the title is same and the
Mm.
picture looks similar.
Mm.
So how people know this is this hybrid, this is still. This is,
Maybe I can put a picture on the left side, so people.
yeah,
know.
yeah. So
Mm.
people look at this slide first time. So
Mm.
I mean,
Mm.
it must be なんていうのかな。you must explain more on the slide.
Okay, sensei. Maybe I can put one slide here to put the damper picture, so we know now we are discussing about which damper.
Okay, yeah, but you have only 8 minutes, so.
I will practice.
Okay.
Okay. And then I discuss about conclusions. And this just
No,
reference.
I mean, this character is so small.
This one?
Yeah,
Okay.
yeah, it's so small. I cannot, I mean, people don't have
Cannot.
time to read it. So just the keyword is okay.
Okay, understand.
Or you highlight the important word
Mhm.
by putting some color.
Right.
But anyway, the size of font size is too small.
Okay, this.
And what is the last one?
Last is just conclusion. This is just reference.
Reference, you don't need to show
No need to show.
because you want to explain the reference, right?
Yes.
It's nothing to do with presentation.
Okay, since.
Okay, please practice
Right.
and please make it 8 minutes.
Okay, since.
Start.
Right.
And also, please put the slide number
Mm.
at the corner.
Okay, since. Right.
Yeah.
Mm.
Okay. Okay.
Thank you so much, Sensei.
I have some, I want to show something. So this is a paper, viscous friction series damper.
Mm.
Actually, it is written by the people from Oilers company.
Mhm.
But Oilers company doesn't produce viscoelastic. This is a combination of, let's see, oil damper left side
Mhm.
and friction damper right side,
Mm.
and in the same direction.
Okay.
But the concept is similar
Mhm.
because oil damper, how to say, has an oval shape,
Mm.
for force deformation oval shape. And if damping force is exceed friction force, it will be upper and lower limit
Okay.
by the friction force. So let's see. Okay. So the upper limit and lower limit is this is a friction capacity.
Right.
And inside this oval shape is like a oil damper hysteresis. Okay. And this is some analysis. They also do some experiment.
Mm.
So before friction damper move, only oil damper moving. Okay, so the
Okay.
hysteresis in the middle is oval shape.
Mm.
And once damping force reach friction force, friction damper start to slide. Okay? So
Yes.
the force doesn't, how to say, larger. There's an upper limit and lower limit. So it looks very similar purpose of our damper. So I'm happy, I mean, people think same purpose.
Okay.
Okay. Also, I have one more paper,
Mhm.
and actually, it is not published.
Mhm.
It is under review. I was asked to review this paper, and I was surprised. Yeah? It is a viscoelastic friction damper.
Okay.
So very similar to our concept,
Mhm.
but they combine in this way. Yeah?
Ah.
Friction damper is the upper side,
Mhm.
and viscoelastic material is this black part.
Right.
So it's not in the middle of coupling beam.
Mm.
It is a head of brace.
Right.
So they arrange this brace
Mhm.
in the building, and some formula. Let me see. Yeah. So only viscoelastic material, the hysteresis is, as you can see, most left figure.
Mm.
It's a kind of oval shape. But if you have a friction force, a friction damper is this red hysteresis. It looks like a box. But the upper and lower limit, it is a friction force.
Okay.
So if you combine viscoelastic damper and friction damper, the total hysteresis will be somehow, how to say, and the hysteresis which has an upper and lower bound.
Mm.
And what's this? Yeah. So viscoelastic damper is oval shape
Yes.
combined with friction damper, friction device. So, なんていうのかな. So our idea to connect friction damper and viscoelastic damper is not original.
Mm.
Yeah, I was a little bit surprised. But fortunately, it's not used for coupling beam.
Mm.
And yeah, so hysteresis is something like this. So, well, black part in the middle is a hysteresis of only viscoelastic, and upper and lower bound is determined by friction damper. Yeah, so they change friction force. Yeah, so, なんていうのかな。It's not our new idea to combine two dampers. So already there are many, I don't know many, but this paper discuss about similar idea. I can send you this paper to you, but don't share with other people
Yes.
because this is under review now.
I also find one paper discussing about viscoelastic and friction damper configuration.
Oh, do you have
But yes, but it's not coupling. It's not coupling wall. It's also same like this. Bracing type.
Do you have a paper now?
Yes, I can show you.
Maybe same author. Yeah?
It's from Yuki Sensei.
Yuki?
From Yuki, United States, London.
UK.
UK. This is a paper. Study viscoelastic and friction damper. And
I have seen this one.
this one. That's the picture. It looks like this.
Yeah. but I couldn't understand how it is.
Yeah, I also didn't. The friction damper. They say this is friction damper,
Mhm.
and sliding is on this side.
Uh-huh.
I also couldn't really understand their concept.
Mm.
Yeah.
That's good. So, which part is viscoelastic material?
Friction damper is this. So detail of diagonal. It should be in this tube, sensei,
Really? Mm,
because he say here diagonal viscoelastic.
mm.
That
But there is no picture of the material.
yes, it is. It doesn't show properly where's the viscoelastic layers. This
Mm.
only show these rings, and they also say that the diagonal fractions temple is this one.
Mm. Mm. Okay.
Okay. Right.
And yeah, I also had to send information to Smith Moriko, but they didn't answer me.
Mhm.
I will
About
request the online meeting
mhm.
and maybe sometime next week.
Okay.
Um, いつなるかな ?Let's see. と
Maybe we can do it after conference, sensei.
yeah. So conference is when?
25 on Saturday,
20 what?
25th. 15、25。
25? Saturday.
はい、Saturday。
ちょっと待ってね。Okay. So maybe after the conference, yeah. そしたら、How about in the morning of 27, Monday?
I'm okay, sensei.
Okay.
Mm.
And let's say 9:30 in the morning.
Okay.
Or how about 29?
29 also, I'm free, sensei.
Free?
Yeah.
Okay.
We can discuss something before the meeting.
29. And I'm available maybe 10 o'clock in the morning.
Okay.
Okay. Yeah. So I will propose to have an online meeting that time. Okay. Who is the next today? Ataya-san? Or Sara-san? Sara-san, you have something to show me?
Yes, about the content of thesis.
Yeah. You must decide the title of your thesis, right?
You
Yeah.
must?
Thesis.
Yeah. Can you see
Yeah.
this slide? Okay. The title is this displacement-based design method of reinforced concrete coupled shear walls, structural performance with the viscous statement.
Oh, okay. And design method, the potential was maybe you can delete performance.
Performance.
So
Okay.
displacement-based design method of reinforced concrete coupled shear wall structures shear wall structures or shear walls. Shear wall maybe shear wall structure is okay. And with viscoelastic damper. So maybe you should delete performance. Okay.
And,
And what is
first, the abstract and acknowledgement table of the content, list of figures, list of tablets, and last one is list of symbols. And including the list of table of contents, first one is chapter 1, it is introduction, including the background, problem statement, and research objectives. And chapter 2 is characteristics of a reinforced concrete shear wall and the displacement design, basic design method. The first are characters of the RC coupling wall and including coupled shear wall behavior, and final one is structured image mechanism. And second, the performance with the steel coupling beam with the different wall lengths. And third one is degree of coupling of coupled shear walls. And fourth is theory of displacement basic design method. And chapter 3 is application of viscoelastic in coupled shear wall structure. First one, of course, the introduction of viscoelastic damper, and the second, the effective stiffness and the damping constant viscoelastic. And third, theory and the equation, and fourth, hysteresis, and final one is installation. Chapter 4 is a numerical analysis results of the reinforced concrete shear wall system with displacement basic design method. The first one is an introduction and model analysis method in stereo 3D. And the third one is a displacement basic design method. And final one, T-shape. And chapter 3 is summary and future research target.
Could you go up? Chapter 3, okay. Why chapter 3 has 4.1? It must be 3.1.
Yeah.
And chapter 4, you put 3.1, but it must be 4.1.
Okay, I see.
And okay. Maybe you can put one more set. I mean, input ground motion in chapter 5. No, chapter 4. You must explain input ground motion before time history analysis.
Okay, I see.
Okay. So please start writing.
Okay, thank you. Can I stop the screen share?
Okay, yeah.
Thank you, Sensei.
So, Hatayo-san, you are next. You also must prepare the presentation, right?
Yeah, thank you.
Did you make a slide, PowerPoint?
Yes, thank you. I made some slides, but before, there's something that I did. These are two models. One is 7 story and one is 25 story something. I considered this just on the X direction to 4.7. All floors are 2D rigid, but the floor that I installed CMD is flexible. And here XY direction only 3, 4, 5, 6, 7, 8.
Okay.
So if it is okay, then I did a pushover analysis and divided this to three segments, and I found the stiffness for each segment and changed it to periods by this
Okay.
mass of the building.
Mm.
So these are the time periods in this three segments, but the fundamental period founded by Estero is 0.922,
Mm-hmm.
a little bit smaller than the first bit. So I installed 4 TMD tuned with each of these periods. This is an under centro. Without TMD, the black line, then the below is 3 TMD actually, and the best performances with 4 TMD under
Okay.
centro.
Mm-hmm.
Under Kobe, it's also 3 and 4 is better performance, and 2 and single TMD almost didn't decrease the displacement. And on the task also 4 TMD and 3 TMD has better performance, and on the Tohoku, almost all of them has the same performance. I don't know. So actually, when we control the first mode of the building, when we calculate the time period, we should use effective mass, because this much of mass contribute to the first mode, not all of the mass. So if we calculate the first period, it's almost the same as the stereo output, which is very close. So it means that it is okay if you use the effective mass instead of total mass. So I used the effective mass then for these 3 segments. In the origin, and this the first segment, the red line is idealized of that pushover curve, and the black line is the linear pushover analysis. So here is a little bit difference, but if we overlap it, we can overlap it, but it's just only idealized, not completely overlap. This fundamental period by Estero, this is the black line, it is very close, and it is the red line, also a little bit larger, but almost all of them the same. So I used that method for effective mass to calculate the period for these 3 segments. Then this is fundamental period, blue line. Green line is a single TMD, which is tuned to this area 1, can say, in the middle. And the red line is tuned to this area, this segment.
So in this case, you put only 1 TMD.
Yes, Sensei. I compared,
okay.
so it shows that when we tune the TMD, the middle part, this part, it is very important and reduces the displacement much better than these 2 areas. Under the Kobe also the same. It means that area 2 and fundamental period cannot decrease the displacement so much. Under task also, this middle part gives a better result. And under Tohoku also, no, it's a little bit different. Fundamental period gives a better result than other 2. So finally, I added another model, 3 TMD, which each of them is tuned to these 3 segments. So it's almost the same result as this, the single TMD which is into the area 1.
Okay.
And for the Kobe, Taft, and Tohoku, also the same result.
Mm.
It means that TMD almost is,
Mm.
in some cases better result, but
Mm.
in some cases not.
Mm-hmm.
So I used it for 25 history, 25 history also the same result.
Mm.
3TMD and the TMD which is found in the middle part of the pushover curve, there's better result, red and green line, red and green line.
Mm.
For Taft and Kobe also red and green line.
Mm.
Green line is turned to the middle part and red line is DTMD which is turned to the both three parts.
Mm-hmm.
And that's all.
Okay, very good. Mm. Yeah, you can write one paper about this. Mm.
Okay, thank you. I will take it. And it's just not completely complete. This is the GES center.
Mm.
I don't know if this parts are okay. I'm just don't know that this.
It's okay. It's okay.
So this is the content, introduction, literature review, objectives, methodology, results, and discussion on further work.
Mm.
It's a little bit introduction about how single TMD is and how multiple TMD is, and which are the key factors in multiple TMD, which is mass ratio, damping ratio, and frequency ratio.
Mm-hmm.
So this is the literature review. This three, actually there are a lot, but it's three here which use the mass distribution, modal mass, equal mass, and also equal mass. So this is the objective.
Mm-hmm.
That's why I use participation factor and effective mass ratio for mass allocation, because participation factor shows the ratio of contribution of oid modes to the total ground acceleration, and effective mass ratio provides insight into how much of the total mass is involved in a specific mode.
Ataya-san, this is not, I mean, about, how to say, could you explain what you have done? This is just, it's like
mass
a
allocation method
textbook.
based on effective mass ratio and participation factor.
Uh-huh.
This is I allocated mass to each TMD. Those TMDs are responsible for different modes, and mass allocation is conducted based on effective mass ratio and participation
But you must
factor.
explain what kind of building you are talking about. Where is the building?
I said here since linear dynamic alloys is using landmass model. Okay. This is the procedure.
No, people don't understand this slide. I mean, people must have an image of the building.
Okay, I will include the building sensor. So here
Where's the picture of the building?
the picture of building sensor here is an
There is no building.
animation sensor.
Uh-huh. Oh, it looks good, but maybe you should have more, I mean, you have a lumped mass model?
Yes, sensor.
So first you must building with models as a lumped mass model, and the TMD is attached to where, and you discuss how to distribute mass value, right?
Okay,
Right.
sensor. Then I will gave a picture like this
Uh-huh.
for TMD,
Oh,
and I say that
this is a little bit not, I mean, realistic. Yeah, it's okay.
yes,
It's
Sensei,
okay.
but we can explain that we just maximize the behavior,
Uh-huh.
but it shows the behavior very good because it shows that without TMD it is not the displacement is too much and
Hmm.
not relaxed. It shows that how the TMDs affected the vibration of the building.
Yeah. Well, this is a stress read analysis, but in real building, you cannot put the TMD. It looks like a cantilever.
Yes, and it's just a model like many researchers use like this model. This is not the real building, it's just a model. So then I will include a picture of the model here, Sensei.
Yeah.
Okay, Sensei, and this is the 3 methods of mass allocation to each TMD.
Uh-huh.
It's equal mass is based on modal mass, and this is based on participation factor and effective mass ratio.
Okay.
So this is the method that
So you have method ABC. Okay. And could you go to next slide?
so this is the result for 7 story, which shows that if black line is actually the single TMD, but this three blue, green, and red lines are for 3 methods of mass allocation, which in each case mass allocation based on participation factor and effective mass ratio is better, red line.
So from here, what is your conclusion? Which one is better? Blue one?
Green line is a reduction percentage. This much, for example, about 50% reduce the displacement, but this two methods about 20% reduce the displacement. So red line is better than these two.
Reduction percentage. What is the meaning of black line?
Black line is single TMD.
Single TMD. Could you go back your slide? Which one is single TMD?
Single TMD is not here, it's multiple TMD into this tree.
And how many TMD? How many TMD you put? Method
Three,
ABC.
Sensei.
Hmm?
Three TMD to control the first 3 modes.
But you didn't mention here.
Yes, Sensei, I didn't mention.
And where is the location of TMD?
I just explained here a little, but there's no figure. We use the maximum amplitude of the corresponding mode to install the location, the location of the
People
TMD.
don't understand. You have only 8 minutes.
Okay, Sensei, then I will put a figure, Sensei.
Please think about people first time look this slide. And do you think people understand what you're doing?
Actually, because the time is limited, maybe not.
So you must use a picture.
Okay,
Okay.
Sensei.
And the people can understand the picture at the first sight. And
Okay,
if you have 3 mass, you must make a picture with 3 mass TMD.
Okay, Sensei.
Okay. So don't show the equation. People don't understand the equation.
Okay, Sensei. So I will modify it and I will show it, Sensei, maybe face to face in your office. I don't know, next week.
Yeah, if you modify the slide, please contact me.
Okay, Sensei.
Yeah. And what is this one? You have 7 story and 20 story.
It's only that one story, Sensei. Yeah, I have two. Yeah, 7 story and 20 story, but this figure is for 20 story.
So also you must show the slide with 7-story building with 3 TMD and 20-story building with 3 TMD. Okay, it's clear if you show the picture. Otherwise, people don't understand.
Okay, Sensei.
Okay.
And this is the conclusion.
Okay.
And this is the further work. I don't know if it is needed,
No, it's not necessary.
so I will delete it. Sensei,
Yeah, you can delete it. Yeah.
and finish. Sensei.
Yeah. Okay. Okay. Ahmed-san, do you have anything you can show me today?
Today, no, Sensei.
No? So. Okay. Okay, so let's discuss next meeting, maybe. So 27 or 29 in the morning, I will ask Sumito Moriko to have a meeting. Maybe we can do control group meeting at the same time. Okay?
Okay, Sensei.
So I will inform you after discussing with Sumito Moriko.
Right.
Okay? And today we have a Oriental Consultant, company will come, 4 o'clock. I hope everyone will join.
I will join, Sensei.
Ataya-san, also you are in the list, right? Ahmed-san, you will join?
Yes, sure,
Please,
Sensei.
please. Sarah-san, how about you?
Yes, I'm John.
Okay, please. Maybe they will give you pencil. I don't know. Some gift or nothing. I don't know. But anyway, the presentation will be very interesting. Okay. So shall we finish?
Right.
Yeah. So see you.
Thank you, Sensei.
Bye.